right, ladies and gentlemen, so today we're going to work on kind of putting all this stuff together that we've been working on with scientific notation. This word right here, efficiency, means are you efficient with this? Can you? It's a little bit of extra practice. So you're going to see all the different types of problems here that we've worked on. So we're talking about the mass of a proton, which you're going to learn about in science later this year, is found inside of an atom. And it's obviously really, really tiny because it's in kilograms. So they want us to write it in scientific notation. So my decimal point has to go from here all the way over to here. So 1.672622 times 10, and I know my exponent is going to be negative because it started off as this really tiny decimal. So when I start counting, 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 27. So negative 27, right? Really, really tiny. The mass of an electron, which again is found within an atom of an element, and you'll learn about those in science later on this year. So now we're going to go from here to here, so that's 9.10938291 times 10, and when I count my decimal points, I'm not going to say that out loud, but it turns out to be to the negative 31 power. Compare the mass of a proton to the mass of an electron. Which one is smaller? The smaller one is going to have the smaller exponent, right? It's a smaller base of 10. So the one that's smaller is the electron. And why? Because negative 31, 10 to the negative 31st, is smaller than 10 to the negative 27. All right, number 3. Compute how many times heavier a proton is than an electron. So this is where we're going to do our division. So we're going to put our neutron on top, 1.672622 times 10 to the negative 27, divided by 9.10938291 times 10 to the negative 31st. And this is what we practiced the other day. So we're going to divide these two, and then we subtract our exponents. And I'm going to round this a little bit because it does turn out to keep going on. So I'm going to take it to 3 decimal places. So when I divide this, it's 0.184. Again, I rounded it, times 10. And if I do negative 27 to negative 31 minus negative 31, that gives me positive 4. We're checking, is this in correct scientific notation? It is not. So I have to go one spot over, 1.84. And since I went to the right, that's decreasing, times 10 to the 3rd. Okay? All right. Next, the geographic area of California is that, and the geographic area of the U.S. is that. Let's round each of these figures off. So this is California, and then this is the U.S. In terms of area, roughly estimate how many Californias would make up one U.S. So this is another division problem. So we're going to take the U.S., 3.794 times 10 to the 6, divide it by 1.637 times 10 to the 5th, divide those, subtract those. Oh, I wrote 7th instead of 5th. I'm sorry. I'm wondering why that didn't seem right. Okay, so when I divide those out, we're going to get approximately 2.32. And again, I rounded. Times 10, and when I subtract 6 and 5, you're going to get 10 to the 1st. So this is correct scientific notation. So in other words, it's going to be about 23 Californias will fit into the entire U.S. All right, so, which is about 23 Californias. Okay. The U.S. national debt as of March was rounded to the nearest dollar. According to the 2012 U.S. Census, there are about that many U.S. citizens. What is each person's share of the debt? So we're going to take and write these in scientific notation. I'm going to round these to the, since it says approximate, right? I'm going to round these to the nearest billion. So I'm going to take this number, the 16, if I round it to the nearest billion, it's 1.6755. And if I take, which if I write in scientific notation is 1.675, oops. Okay, my pen's not working, sorry. 55 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yep, 13, I hope. And for the US population, if I round that, or to the number of people, if I round that to the nearest billion, it's 314 billion. Yeah, look at that, that's horrible. But anyway, so then we're going to divide these. 3.14 times 10 to the 8th. So now we're going to divide and we're going to subtract. And again, we are going to approximate. When I divide this, I get about 0.5336 times 10 to the 5th. Well, if they want that in real dollars, first of all, in correct scientific notation, it's times 10 to the 4th, which means each person's share of the debt, if I write that in standard form, is $53,360. Okay, next page. So just some kind of, well, I don't know if useful is the right term, but we're talking about the distance from the Earth to the Moon and the distance from Earth to Mars. We want to know how much further. So this is a subtraction problem. So conveniently, these are already written in scientific notation. So 9.24 times 10 to the 7th minus 3.84 times 10 to the 5th. And this is where I have to get my powers, or my exponents to match. So I'm going to turn the smaller one into the 7th. So I'm going to keep my 9.24 times 10 to the 7th. I'm going to go 2 places over. So 0.0384 times 10 to the 7th. And subtract those. So I have to put in a couple zeros here. So that's going to give me a 6, a 1, a 0, 2, 9.2016 times 10 to the 7th. Okay? What are the advantages of using scientific notation when computing these types of problems? It makes it easier to add, subtract, multiply, or divide large numbers. Sometimes, if you understand how to use your calculators, larger or smaller. Okay, any questions? Bring them to class. Have a good day.